Hello, everyone. We're back for part 2 of chapter 13, Solutions. This set of slides, or like part 2 here, focuses a bit more on how solutions affect our life. So the beginning part of the chapter kind of went through some of the basics of how solutions, like we talk about them, how we talk about how strong they are, and stuff like that. However, here we're going to figure out all the different ways we interact with solutions and how they affect our lives throughout. So sit back, relax, and enjoy. So, water. Now with electrolytes. Sound like an advertisement, right? But have you ever bought a sports drink that says it has electrolytes to replenish what is lost in your body during a workout? You know, like, I don't know, Gatorade or Propel, I don't know, or something, right? Why do sports drinks or waters often contain electrolytes, and like what are electrolytes? Okay, so an electrolyte solution occurs when an ionic solid is dissolved in water. So we've already kind of talked about some of this information a little bit here, but remember, when water dissolves an ionic compound versus when it dissolves a molecular compound, in an ionic compound, it's going to pull apart each of those ions. Remember, the ions are only held together through a positive and negative attraction, so that polar water molecule with a positive and negative end can kind of line up and pull apart all of those different little ions. And so those water molecules are more attracted to the individual ions than they are to each other, so it's able to like kind of break those interactions and form new ones with the ions in the water rather than the ions in each other. So this puts these charged ions in solution, and actually electrolyte solutions conduct electricity, whereas pure water, if you just had pure water with nothing in it, it's actually not a very good conductor in the end. However, the reason water can shock you and stuff like that is because lots of times it has these salts and these ions dissolved in it. So therefore, those ions are what are able to pass around electrons to make it, to make it conduct electricity. So it's actually the salt ions in water that conduct electricity in water. And so some of these ions, like sodium and potassium, can be lost during a workout when you sweat. So taking them back in can help you to replenish what you lost. So that's kind of the big idea with electrolytes. Like if you're out kind of choosing to buy a sports drink or you're choosing something, that's what they mean. So taking in extra probably isn't going to do anything for you. It's going to pass through your body. However, again, if you've had like a hard workout, you've lost a lot of sweat, you're like, I need to get it back in. Electrolytes and electrolyte drinks like that are a great way to do that. Of course, make your own health choices, though. We all know, chemist, not doctor, doesn't even have PhD. So I got a master's. So anyways, we have a non-electrolyte solution, is kind of the other option. So that's what happens when a molecular compound is dissolved in water. So when a molecular compound is dissolved in water, we talked about this a little bit before, it's just going to pull apart the molecules from each other. So it's going to be that full molecule in there. So in the picture here, you can see up here in the electrolyte solution, we have all the positive and negative ions separated from each other. Whereas in a non-electrolyte solution, that solution with a molecular compound that's been dissolved, you don't have those charged particles, and you don't have like pieces of the molecule or something, for example. You just have the whole molecule being broken apart. So if you have a sugar cube, it's like, okay, 1 sugar molecule, 2 sugar molecules, 3 sugar molecules. So you can pull apart a molecular compound, and it stays as its compound self, but it's just those molecules floating around in the water. So this is, for example, like sugar water I mentioned before. So this is what happens when you dissolve sugar in water versus this is what happens when you dissolve salt in water. So non-electrolyte solutions don't generally conduct electricity because, again, it's those ions that are able to pass around the electrons to conduct electricity. And sugar water is, again, an example of a non-electrolyte solution. So here we're just worried about knowing the difference between an electrolyte solution that is formed by ionic compounds being dissolved. It puts those ions in solution, so therefore has different properties than a non-electrolyte solution that has molecular compounds that just has those molecules in solution. So that's why we drink electrolytes in our sports drinks sometimes. So my question here at the top, even though it's hidden behind me a little bit on your screen, is what do warm pop and deadly burping lakes have in common? Did you know lakes could burp? So again, obvious answer, burps. Pop, burping lake, burps. But let's think about the less obvious answer here about what they might have in common. So what I want to talk to you about is the solubility of gases, okay? So we talked a little bit in part 1 about how you could have all those different phases dissolved into each other. So thus far, we've been kind of thinking about maybe diluting a liquid with water, so 2 liquids, or we've been thinking about putting a salt or a molecular compound into water, which is going to be a solid into a liquid. Here, we're talking about the solubility of a gas into a liquid, okay? So I've got 2 points to make here about this. So the solubility of gases into liquids increases when temperature goes down. So this is going to be the opposite for solids that we're going to talk about in just a minute here, okay? But the solubility of gas decreases when temperature goes down. So remember what happens to gas molecules when they are decreased in temperature. Those molecules slow down. They're not moving quite so fast flying around. This gives them more time to interact with like the surface of the liquid and to be pulled in and dissolved and to form those interactions that pull that gas into that liquid. So if it has more time to interact with the surface of the liquid because it's moving much slower, it's going to be more easily dissolved. And the other thing that the solubility of a gas depends upon is pressure. Of course, right? So if you increase the pressure above a liquid, a gas is going to become more soluble, right? So if you're increasing the pressure, you're either decreasing the volume, maybe you've got a higher number of particles or something like that, but that increased pressure forces the gas molecules to interact with the liquid more often. They're going to have to spend more time, again, interacting with the liquid, again, much more easy to be pulled in and dissolved. So keep that in mind. So if you want your pop to stay bubbly, keep it closed and keep it cold. So if you decrease the pressure by opening your pop can, you're going to let that pressure out so that gas can more easily come out of solution because it's not a bunch of molecules pressing down on the surface of the liquid saying, okay, one comes out, one's going to go right back in because it has such a high pressure and if you keep it cold, such a cold temperature. But if you crack that pressure and you let your pop warm up, all of the carbon dioxide bubbles are going to escape because, again, that gas is going to have its motion increased when temperature increases. So as you heat it up, those molecules are going to come out, those gas molecules are going to come out of solution as well. So again, if you open your pop and you leave it sitting on the counter, it's going to go much flatter than if you, let's say, for example, open it and set it in the fridge. I am ridiculous. I don't really like carbonation. So I will do stuff like this. I will open my pop and set it on my desk for a little bit before I choose to drink it because I want that carbonation to come out of solution. Well, I don't usually let it warm up, but I might open a pop and set it in the fridge for like a day or two if I have plans to drink one later because I want my pop to go just a little bit more flat, but not totally flat. So I leverage these things every day in my life, at least. So maybe you'll do the opposite. You'll make sure that you keep your pop closed and in the fridge then. It's also probably why a can will go faster than a bottle because you can kind of hold that pressure in if you screw that bottle cap on. Tangent. Let's talk about burping lakes. I built that up. Deadly burping lakes. What am I talking about? So if you read the first section in the book or you read kind of throughout the entire chapter, they keep talking about Lake Nyos in Cameroon, Africa. So this lake actually is a volcanic crater. So it's a volcanic crater that's been filled with water. The thing is, though, is a lot of the volcanic gases are carbon dioxide. So the thing is the pressure and weight of all this water sitting on top of those gases allows the carbon dioxide to be dissolved into the water of the lake. So usually it's just in the water of the lake, doesn't really disturb much. It sits down at the bottom where it's going to have a much higher pressure sitting on top of it. So that's kind of how it sits. However, in some cases, if the lake bed is disturbed or you disturb the amount of pressure that's sitting over top of the lake bed, it will release that carbon dioxide because now we've changed the pressure. So the solubility of that carbon dioxide has changed. So therefore, what happened was one day, the pressure on the lake bed was changed, and the gas or the lake burped, released a ton of that carbon dioxide, and genuinely, unfortunately, a lot of people in the area were affected, and a lot of people passed away because of this. Now they have scientists and engineers that go out and constantly, or every now and again, release that carbon dioxide in safe amounts so that something like this doesn't happen again. We don't have an unexpected shift in pressure that causes the solubility of the gas to change that can literally, in this case, be deadly. So this stuff matters, man. So I might be making jokes about warm pop and deadly burping lakes, but we have to actively monitor stuff like this to make sure that people are safe. So we always are thinking about the solubility of gases. So I'm going to move my video so you can see my next point because I kind of like it. So have you ever wondered why you can't make real sweet tea by dissolving sugar in cold iced tea? A lot of times in the Midwest, at least, or tending to be up towards the north, sweet tea is a very southern thing. Oftentimes, if you go to a restaurant and you ask for sweet tea, they'll say, oh, we have iced tea, and here, have some sugar packets, make yourself sweet tea. Well, this is why you can't really do that. So the reason this doesn't really work well has to do with the level of solubility that solids exhibit in different temperatures of solution. So gases depend on both temperature and pressure. However, solids just depend upon temperature. So in general, this isn't the case for every single solid out there, but just in general, what we're going to consider for this class is that solids are more soluble in water than in higher temperature, or are more soluble in water in higher temperatures. Solids are more soluble in water in higher temperatures. Again, it depends upon the solid, and then for some solids, this effect is greater. So it doesn't change a whole lot with like NaCl, for example. However, you can see a huge shift with KNO3, for example. So the higher the temperature, the more solid that can be dissolved into water. So when you make real sweet tea, like they do in the South, you brew the tea hot and you add the sugar while the tea is still hot. So as a kid, I remember making what my parents and I called sun tea. So in the summer, we would take a pitcher of water, we'd throw a bunch of tea bags in there, we would throw a bunch of sugar in there, and we'd set it outside for a day, and we would let the sun heat the tea up, dissolve the sugar, and make us sweet tea. So try it. It's quite nice. So this way, if you heat the tea up first and then you add the sugar, you're able to dissolve more sugar into the tea, and then we can cool it for drinking, and that sugar will generally stay in solution. Some of it will fall back out, but not a ton. So generally that sugar stays in solution, so we can have cold sweet tea, which is my favorite. So the next time someone offers you iced tea with sugar packets instead of sweet tea, tell them chemistry says you can't make sweet tea with a cold drink. Or you can tell them Professor Thomas says that, but more fun if you say chemistry. So you can't make sweet tea with a cold drink because you cannot dissolve the sugar in the same way, because the solubility of a solid depends upon the temperature. You're not going to get as much sugar into the actual tea liquid itself if you put it in a cold tea versus if you put it in a hot tea. So, delish. This whole one has a bunch of food themes in it. Oh well. So what I want to know now is, have you ever had rock candy? So I'm not sure if you've seen this before. I have a picture of your screen of rock candy being made, but generally it's a stick and it has crystallized sugar on the outside of the stick. Sometimes we add food coloring like you see here, or we add flavors to our rock candy as well. So it's just a sweet sugar candy that's pure sugar that attaches itself to a stick or string or something, and then you can eat the sugar and whatever flavoring we choose to put into it. So if you've ever wondered how rock candy is made, it actually has to deal with the amount of solute in solution and how you can get the maximum amount of solute into solution. So first and foremost, we got to talk about unsaturated solutions. So unsaturated solutions hold less than the maximum amount of solute in concentration or solute in solution in the conditions present. So basically what I'm trying to say here is like you haven't maxed out your level of solute. So at some point you're going to reach a breaking point. Like if I took this like whole jar of salt here, if I took this whole thing of salt and I put it in about a cup of water, you're going to see that there's still going to be salt in the bottom of the glass that isn't actually dissolved. So when you hit that breaking point, you can't put any more into solution. You have all of the salt particles dissolved that those water molecules can handle, for example. So those water molecules in a certain sample, you only have so many water molecules to be able to interact with and pull apart those ions. So in an unsaturated solution, you could still add more and that water could still pull apart the ions. However, in a saturated solution, that's where you've reached that like sweet spot, that exact maximum amount of solute in solution. So in a saturated solution, you have exactly the amount of molecules or ions that the amount of water that you have can pull apart and handle, basically, and kind of keep up in solution. And so what I'm saying here, in the conditions present, remember, the solubility of a solid, as we just talked about, depends upon temperature. So if I'm talking about unsaturated and saturated solutions, this all depends upon temperature as well. So you can also make a supersaturated solution if you think about how temperature interacts with solubility. So supersaturated solutions hold more than the normal maximum amount of solute in solution in the conditions present. So basically, to make a supersaturated solution, what you do is you heat up something like salt water, for example, and you keep adding the more salt as it becomes more soluble, right? As temperature increases, solubility increases. So even if I have the same amount of water, if I heat the water in that solution up, I can continue to add more salt to reach that saturation point at each individual temperature. However, if you take that saturated solution and you cool it down with no interruptions, so no imperfections in your glassware, you cannot bump it, an earthquake doesn't exist, you don't breathe on it too hard, you don't talk near it too loud. If you do not disturb it, what will happen at the lower temperature is that all of that goodness, all of those ions will stay in solution still. So even though it should not be that soluble at a cooler temperature, all those ions are staying in solution basically because we haven't done something to force them to leave the solution. So this is actually how we make rock candy in the end. We heat water and sugar and flavoring and color if you wish. We add a string, or in the picture here, it's a stick. And so once we add that stick, we're disturbing our saturated or supersaturated solution, and you start to see some of those salt crystals form on the stick. So if you leave it for long enough, we'll recrystallize that sugar out of solution as it cools. So to make rock candy, we're leveraging these ideas of saturation of solution. So we did talk a bit about concentration, meaning strength, but these are kind of like the maximum versus like the over-the-top maximum amount of solute you can put in. So kind of similar there, but a little bit of a different idea. So that's how rock candy's made, and that is how we can do that. So pretty cool. And our last foray into how solutions benefit us in our everyday life is why do we put salt on the roads in the winter? So we all know that the intention is to keep the roads from freezing over, but why? Why does that happen? Well, generally, in a non-volatile solution, so something that's relatively stable, basically, so in something that's stable, we will have a lower freezing point than the pure liquid, and we call this freezing point depression. So we put salt on the roads because depending upon the salt you use, or depending upon how much salt you use, rather, you can lower the freezing point of water from 32 degrees Fahrenheit, where it usually freezes, right, that we're used to, down to -10. So if you have an inkling that it's going to get really cold and it's snowing or heaven forbid, freezing rain, you're going to want to make sure you put salt or something on the roads to keep the roads from freezing over and causing accidents, right? So again, that's why we're going to put salt on the road, is so that it keeps that ice from freezing over, because now you have these salt ions in solution that are forming different interactions with the water. So we have an entirely different behavior of salt water than we do of pure water. And this is just another example of that. So freezing point depression. A solution will have a lower freezing point than a pure liquid. This is actually how you can freeze a frog and it can stay alive. As certain frogs, their blood kind of acts like antifreeze. Their blood has such a low freezing point from the chemicals that are in it that it keeps it liquid in extreme cold, and frogs can survive stuff like that because of this freezing point depression. And they've evolved through the years to have blood that has the right chemicals in it to keep their blood from freezing. So, pretty cool. The kind of opposite of this, on the other hand, is boiling point elevation. So, we said freezing point goes down, but boiling point is going to go up. So, it kind of creates a larger gap between the freezing point and the boiling point. So, generally, again, those non-volatile solutions, so those more stable solutions, will have a higher boiling point than the pure liquid. So, for example, antifreeze in your engine not only keeps it from freezing in the winter, we just talked about that, freezing point depression, but it can also actually, like, antifreeze is a bit of a misnomer, it'll also keep it from boiling over in the summer. So it'll keep your engine cooler than if you were running regular water. So not only does it keep your engine from freezing in the winter, it's going to raise that boiling point. So when it's really hot here in the summer too, our cars can still handle that situation, or even in hotter areas than where we are. So it's a pretty cool scenario. So again, anytime you have a non-volatile liquid, so a stable solution, you're going to have a lower freezing point than in a pure liquid, and you're going to have a higher boiling point than in a pure liquid. So I hope you enjoyed this short foray into how solutions affect our lives. So I would like you to get to know some of these relationships. That's what I'm going to be looking for you to take away from this, is that things like freezing point depression, boiling point elevation, what those mean, unsaturated, saturated, supersaturated solutions, that relationship between solubility and temperature of solids, the relationship between solubility of gases and temperature and pressure, and then also the difference between an electrolyte solution and a non-electrolyte solution. So that's what I'm looking for you guys to kind of take away from this today. I hope you learned something, and maybe you got some fun facts to kind of, say along the way. Someone might bring up frogs, and you'd be like, I know why frogs don't freeze. It's because their blood works like antifreeze, and antifreeze lowers the freezing, has that freezing point depression, for example. That one's probably not the coolest one. I think all of them are pretty cool. I personally really like the electrolyte solutions. So maybe you can say, hey, I know how those electrolytes work. I know how solids get dissolved into water. Those ions are pulled apart as electrolytes. So share some fun facts with your friends, pass it on. But this is how solutions affect your life.